Okay, you can begin now.
Okay, cool. All right, welcome back, everyone. And this is the second session on post-quantum crypto of Crypto 2020. And there are a couple of talks on not post part, so we'll hear about that. So the first talk, so we'll have 4 talks, and the first one will be Scalable Pseudorandom Quantum States by Omri Shumeli, Zvika Berkeski. And Omri will be giving a talk. Omri, please go ahead and share your slides, and the floor is yours.
Thank you, Feng. Just a moment. Okay, so welcome everyone to this crypto talk on scalable pseudorandom quantum states. I'm Omri Shmueli. This is a joint work with Zvika Berkeski. So in this work, we are going to concentrate on the efficient generation of quantum random states, and it is a basic fact in quantum information theory that efficiently generating a truly random quantum state is impossible, simply because there is too much information in a truly random quantum state and there is no succinct representation. Now, a more modest and achievable goal is aiming for an efficiently assemblable distribution such that for a bounded number of output copies, it is going to be indistinguishable from the same number of copies of a truly random quantum state. And we know, for example, that for one copy, it is trivial. A random classical string is indistinguishable from a random quantum state. And the more copies we are going to let our adversary have, the harder it is going to become for us to sample. And one functionality that implements this approach is called the pseudo-random quantum state. This is an efficiently assemblable distribution such that for any polynomial number of copies of the output states, it is going to be indistinguishable from the same number of copies of a truly random quantum state for polynomial time quantum algorithms. Now, more formally, the definition of a pseudo-random quantum state generators, first produced by Ji Liu and Song in Crypto 2018. This is a polynomial time quantum algorithm. It gets n, the output state size, and k, classical key. And as we can see, for any polynomial number of copies, it's going to be indistinguishable from an n-qubit random quantum state. And it is known to how to construct such generators based on post-quantum one-way functions. Now, one thing that we observe about the security definition of a PRS generator is that the number that we think of as the security parameter in red, which denotes how many copies we are going to let our adversary have and how hard is it going to be to distinguish, and the other number in blue, which is the output state size, these are exactly the same number. And the operational meaning of this is that the more we want to make our output state size, the more we want to make our state random, the bigger it gets. And another thing to say about this is we can say maybe something along these lines. We can take n to be very big, in particular, the security parameter is going to be big, and then take some prefix of this very big quantum state, which we now know is very random, but these kind of strategies don't yield a pure state, and this is the reason that it does not yield a PRS generator. So the question that we are going to try and answer in this work is, can we control the security level independently of the output state size? So more formally, essentially, this is the definition that we are proposing. This is a scalable PRS generator, the exact same algorithm from before, but now it gets 2 independently tunable parameters, and the output state size in blue, and in red, lambda, the security parameter. So a few words in relation to the previous construction. So why doesn't previous constructions have a security parameter? So all of the states in the support of the PRS generator are essentially uniform amplitudes. Like all of the vectors that are in the support are, all of the elements have the same absolute value. And the phases are random. Now, in order to, and one thing to say about these kind of distributions, that for a small number of qubits, the dimension is small and it becomes very easy to distinguish from a truly random small quantum state. and it becomes harder when the dimension grows. And to get a scalable random state where we can look at a small state, but it's still very, very hard to distinguish from a truly random quantum state, we also need to randomize the amplitudes, not only the phases. And the thing is that random phases is a local property and random amplitudes is a global property. What exactly do I mean by this? Is that we can start from any superposition, say the uniform superposition, and in order to randomize the amplitudes, we can make a local computation in superposition, and we can get random phases, sorry. And in order to get random amplitudes, we know that a quantum state corresponds to a unit vector, and a unit vector it means that all of the amplitudes depend on each other because they had to sum up. The square of the amplitudes need to sum up to 1. So in this work, very briefly, we define and explore this notion of scalability. In particular, we show a framework for constructing scalable random quantum objects. We also show a technique for randomizing the amplitudes. And more formally, we show that based on the existence of post-quantum one-way functions, we know how to construct scalable PRS generators. This is the same computational assumption as needed for non-scalable PRS generators. And we also show for another notion of the efficient generation of quantum state, it's called T-design. I did not define it, but it is incomparable to pseudorandom quantum states. And we improve the efficiency of the scalable T-design generators from depending polynomially on T, the number of copies, to depending polylogarithmically on T. And one last word about the technique. So in a very small nutshell, we know that the space of all quantum states corresponds to the unit sphere of if it's an n-qubit quantum state, so in a 2 to the n dimension. And to get a random point on this sphere, we know that a Gaussian vector, a normalized Gaussian vector, is because of the spherical symmetry of the Gaussian distribution, distributes exactly the same. So what essentially we are going to try and do is to sample a Gaussian vector in a quantum state. And one good thing about the Gaussian distribution, we know that it is locally sampleable, which means that we can sample each of the 2 to the n coordinates of this vector independently. And one thing that we need to take care of is the norm. This is the global property, which I referred to earlier, as something that we don't know how to compute efficiently. And in order to get around us not knowing the norm of this 2 to the n dimensional vector, we use a technique called quantum rejection sampling, which is an analog, the quantum analog of classical rejection sampling. And this is how we efficiently generate the quantum state that corresponds to this Gaussian vector. And that's it. Thank you for listening.
Okay, thanks, Omri. And I'll hand it to Dominic to moderate the questions.
Okay, so anyone who has questions on this nice talk, please type your questions in the chat. So either on the, well, in any of the chats you find, or raise your hand. So, I mean, virtually raise your hand. There's a function for that. In the meantime, I have one question. So, so your construction, as I understand, is directly like constructing directly a pseudorandom state instead of doing the wrong approach of cutting off some qubits from an existing state. But I was wondering whether you know the answer is if I'm given a big pseudorandom state and I want to make a smaller one out of it, but I might want to use something more clever than cutting off bits. Do we know that this is impossible in general to kind of?
I don't know of something that will tell us that this is impossible. I surely don't know that this is possible, but I don't know that this is impossible. Yeah.
Okay. Yeah. So it looks like we don't have any other questions right now. So I thank you again for your talk, and I give the microphone back to Fan.
Okay, Thanks, Henri, again. Let's move on to the next talk. So our next talk will be Efficient Pseudorandom Correlation Generators from RIN LPN by Elade Boller, Geoffroy Coteau, Niv Gilbo, Yval Ishay, Lisa Ko, Peter Shou, and Peter will be giving a talk. Peter, the floor is yours.
You see my screen?
Yes.
Great. So this is joint work with Elade, Geoffroy, Niv, Yuval, and Lisa, my co-authors. This talk is a little less quantum. The main motivation is actually towards constructing secure multi-party computation protocols. So here we have two parties, Alice and Bob, with inputs X and Y. They want to run some interactive protocol to evaluate a function f on their private inputs without revealing any more information on their inputs. And in particular, we're looking at an extension of this model where Alice and Bob also have access to, ahead of time, some general source of correlated randomness, which is generated by a trusted dealer independently of their inputs. So the benefits of this pre-processing model are that when the parties use the correlated randomness in the online phase of the protocol, this can now be information theoretically secure and also very efficient in practice. In fact, it's just got a small constant overhead on top of evaluating the function and sending a circuit description of the function in the clear. Now, the main downside of this approach is that the parties actually have to generate this private correlated randomness in the first place. And typically this is done with an interactive protocol, which is very expensive and actually dominates the overall cost of most protocols in practice. Now, a pseudorandom correlation generator is a tool that offers an approach for reducing the cost of this pre-processing phase. Whereas a traditional pseudorandom generator takes a short seed and expands this to a longer pseudorandom string, a pseudorandom correlation generator first samples a pair of short correlated seeds, whereupon each of these seeds can then be locally expanded to produce a larger output, such that the pair of outputs together is supposed to come from some target correlation, where you could think of this as maybe a large batch of oblivious transfers on random inputs, or a large batch of multiplication triples used in an MPC protocol. And the security property of a PCG is that one of these expanded outputs should be computationally indistinguishable from a real sample of the correlation, even if you're given the seed which generated the other output from the PCG. So this can be plugged into any MPC protocol in the pre-processing model, such that the amount of correlated randomness you need can be reduced to a much smaller size. Now, the main goal today is we're going to be looking at generating a correlation called oblivious linear function evaluation and related correlations. So this is a two-party correlation where typically you have an input UV from Bob and an input X from Alice. These are field elements, and Alice receives the output W, which is UX plus V. But here, because we're sampling a correlation, then we just sample the inputs at random and give them out to the parties. Yeah, so this is related to multiplication triples and authenticated multiplication triples, which we also consider in the paper, that are used in as kind of the main type of correlated randomness in a lot of secure computation protocols. So our main contribution is to give new constructions of pseudorandom correlation generators based on variants of the ring learning parity with noise assumption. In particular, we give PCGs for generating oblivious linear function evaluations and multiplication triples, where the computational cost of expanding the seeds to produce n OLEs or triples is just quasi-linear in the length of the output. So this improves upon a previous construction from crypto last year, where we had a quadratic in n cost based on the standard LPN assumption. Now, interestingly, techniques here are somewhat analogous to and also inspired by existing techniques from the fully homomorphic encryption literature, where they switched from using learner with errors to ring LWE to avoid a quadratic blowup in ciphertext size during homomorphic evaluation. So a second main contribution is an actively secure protocol for actually setting up the seeds for these PCGs in a secure manner. And together, these can be plugged in to produce a pre-processing phase for multi-party computation protocols, such as SPEEDS, which is active security. And it gives us something which is very concretely efficient and gives dramatic reductions in bandwidth and storage costs compared with the existing state of the art. So finally, a few more highlights of the paper. We give some extensions of our basic PCGs to the multi-party setting and also more general forms of bilinear correlations, including matrix triples. And finally, we provide some security analysis of the variance of the ring LPN assumption we require. In particular, our most efficient constructions are based on an arithmetic variant of ring LPN over a large prime modulus P and a polynomial modulus f of x, where f of x should split completely into linear factors modulo P. So this is somewhat similar to ring LWE using a cyclotomic polynomial. And here we have a sparse error distribution and also a constant number of samples. So you might be wondering, how efficient is this? Well, in practice, we didn't implement it completely, but here's a few concrete estimates based on some micro benchmarks we did. So if you want to generate 1 million authenticated multiplication triples for the speeds protocol with 2 parties over 128-bit prime field, then the rough pipeline, first you have to start out with a small number of seed triples, say around 25,000, and a few megabytes of communication in the protocol, which generates the first set of PCG seeds. And then the local expansion phase takes around 20 seconds to produce the 1 million triples. And if you want to produce more triples than this, then you can just reserve the last portion of these to do a kind of bootstrapping procedure and use these to generate the seed triples for the next set of PCG seeds. So comparison to the state-of-the-art interactive approaches, which are based on homomorphic encryption, these require distributed key generation setup and a large amount of interaction with a comparable amount of computation time. But notably, the 2 gigabytes of communication that it requires is much, much larger than the amount to set up the PCG seeds, which we use. This shows that PCGs give a practical approach for multiplication triples and other applications, which can be used to greatly reduce bandwidth in applications of secure computation. So that's it, and thanks for listening.
All right, thanks, Peter. And we have time for questions.
Yes, so as before, if you have any questions, please type them in the chat. I have one question. So I guess this ended, this is in the post-quantum session because it is related to learning parity with noise, which is not a quantum broken assumption. But I'm wondering, did you also, is it also post-quantum secure? So does the security proof go through in the quantum setting, or is it just kind of related to post-quantum security by sharing an assumption?
So we didn't think about doing any security proofs in the post-quantum session. And I think for our main protocol, we do rely on a random oracle, which may be a little more tricky for post-quantum's adversary, I guess.
Okay, I see, yeah.
Dominic, you're muted.
Oh, yeah, thanks. I was just saying, it seems we don't have any more questions, so I thank you for your talk and give the mic back to Fang.
Okay, thanks.
Okay, thanks. All right, let's move on to the next talk. So this will be a non-PCP approach to succinct quantum safe zero knowledge by Jonathan Bootle, Vadim Lubashevsky, Kang Wing, Gregor Seiler, and Kang will be giving the talk. Kang, please go ahead.
Thank you very much for the introduction. Let me share the screen. Okay, can you see it?
Yep, we're good.
Great. Okay, so hi everyone. My name is Khan. I'm a PhD student at IBM Research Zurich, and today I'm going to talk about a non-PCP approach to succinct quantum safe zero knowledge. So this is joint work with Jonathan Bootle, Vadim Lubashevsky, and Gregor Seiler. Okay, so this approach is related to lattice-based zero knowledge proofs. So here's just a simple example of the statement, the classical one. So you're given a matrix A, the vector U, and you want to prove knowledge of a short vector S, meaning with small coefficients, such that AS is equal to U mod Q, where Q is a prime. So these types of statements can be proven obviously using lattice commitments, and there have been a lot of works on that, especially Gregor's talk on Monday. So they rely on presumably quantum state assumption like sys or LWE, and also they can be implemented efficiently, well, for addition and multiplication, and also in the polynomial ring setting with the entities. So the main drawback, as also described by Gregor on Monday, is that the proof size is linear in the number of commitments. So maybe it's still fine to apply these techniques to prove some small statements like range proof or proving knowledge of LWE sample. But one can imagine that for more complicated statements, the proof size can basically blow. Then on the other hand, we have the more generic approach, which is the PCP, like Aurora or Ligero. They rely on collision resistant hash functions, and then the proof size is really sublinear or even logarithmic in some cases. So then the downside is that it's quite slower compared to the lattices, and sometimes this might be, in some scenarios, this might be very essential. For example, when we want to run protocols on constrained devices and so on. So the main motivation of this paper is to construct purely lattice-based zero-knowledge proofs so that they can be implemented efficiently, but they also have the nice sublinear proof size. So kind of benefits of the two worlds. So this is the motivation. So our contributions can be split into basically two protocols. So they have two different techniques. They are sublinear. And yeah, I don't really have time to discuss both of them, unfortunately. So I find the level commitment very interesting. So I'm also happy to talk about it offline. It's also in the video, but in this talk, we'll just focus on the main idea of the lattice-based bullet proofs. Okay, so it is inspired by the discrete log bullet proofs, as the name suggests. So the main observation is as follows. So suppose we have some problem introduced in the previous slide. So we have AS is equal to U, where it holds over some ring. And let's say the vector S, the secret vector S, is very long. So the length is very long, and it has small coefficients. So obviously one could just do some, apply some well-known techniques to prove that, like Fiat-Shamir with aborts. But you can see that if you just do something like that, then you send the masked opening of S, which has the same length as S. So if S is very long, then this part would be very expensive. So the main idea of bulletproofs is of the lattice-based bulletproofs is the following. So we split the matrix A into two submatrices, A0 and A1, then the vector S into S0 and S1 of the equal length. Then we have A0, A1 times S0, S1 is U. So then for a challenge C, get challenge, that we have the following. So the matrix CA0 plus A1 times the matrix S0 plus CS1 is equal to some W0 plus CU plus C squared W1. So here the W's are the cross terms. So W0 is A1 S0 and W1 is A0 S1. So the intuition is just to send W0 and W1 to the verifier. So you can see from that it's not really zero knowledge. And then we end up proving a kind of similar equation. So the equation at the top can be written as BS prime is equal to U prime. So B here is the matrix CA0 plus A1. S prime is the secret vector S0 plus CS1. And U prime is the vector W0 plus CU plus C squared W1, which is public. So from A0, AS is equal to U, we ended up with BS prime is equal to U prime. So what's the difference here? So that's the good news and the bad news. So the good news is that the length of the secret vector S prime is two times shorter than S. So you can imagine this as one round, but we can apply multiple rounds to get even smaller sizes, smaller length of the secret vector. So that at the end, when the length is not very big, then we can send a mass opening and just like before. Okay, so the bad news here, like you can see from the slide, is that we assume that the S, so S0 and S1 have small coefficients, right? But then S prime, which is S0 plus CS1, will have bigger coefficient than S. assuming that C is small. So this is just for one round. So if we have many rounds, like logarithmically many rounds, then you can imagine that this secret vector S prime will be quite will be bigger. And then when we do the soundness proof, then we extract, then the size also grows. And then for that, we have to set the parameters like prime modulus and so on. So the main conclusion is that even though the proof size is nice and so on, the extracted message being large makes the protocol not really interesting in practice. So here I pointed out the advantages and disadvantages of these two protocols. So I didn't talk really about level commitments, but for lattice-based Boolean proofs, we get the polylogarithmic size. It is not zero knowledge because we send these W's. And then there is this massive slack, meaning that when you extract the vector, then the secret vector, then the sizes of that, the coefficients of the extracted vector are much bigger than the one that we started with. So, well, okay, so nevertheless, I think this is a nice theoretical first step towards practical sublinear quantum state zero knowledge proofs. So yeah, thank you very much for listening.
All right, thanks, Khan. Are there any questions for Khan?
I have one little question. Have you made any, like, do you have any concrete comparisons how this compares to other protocols, like, or implementation experiments or something?
So for these two protocols, like we noticed that the slack is so big that we think that it's, in terms of techniques, we think they are nice, but in terms of the sizes, even asymptotically, I'm not sure if there's any point to instantiate that.
I see. So it's probably a stepping stone towards future things.
Yeah.
Cool. Okay. Any other questions from the audience?
Just to add, I think.
Oh, sorry. No, go ahead.
I think the question that you asked about if the protocol itself is post-quantum in the previous talk, it can be really, it is also a very nice question here. So I just wanted to point out that this bulletproofs technique was also analyzed in yesterday's talk on zero knowledge. So this multi-round Fiat-Shamir paper also discussed that lattice-based bulletproofs in the paper.
I see. Cool.
Okay, so that one can be applied here to remove the interaction. That's what you mean?
It's about how to prove that the protocol is secure in QROM. That's what I mean.
Oh, okay.
Okay, so it seems we don't have any other questions, so I give the mic back to Fan.
Okay, excellent. All right, now we have our last talk in this session. It's non-interactive zero-knowledge arguments for QMA with pre-processing by Andrea Coladangelo, Thomas Vidic, Tina Jen, and Andrea will be giving the talk. Andrea, the floor is yours.
Can you hear me and can you see the screen?
Yep.
Okay, good. So this will be a brief overview of joint work with Tina Zhang and Thomas Vidic. So non-interactive zero-knowledge proofs are, of course, well studied in the classical literature. And it is well known that in the, hold on. There you go. It's well known that in the plain model, these are impossible to achieve for languages outside of BPP. And one of the most common setups to overcome this and to get non-interactive zero-knowledge proofs for all of NP is to assume that the verifier and the prover share a common random string or common reference string. Now, this work is about the quantum setting. So in the quantum setting, the first question we can ask is, are our proofs for NP, even the interactive ones, still sound and zero knowledge? So in particular, what happens when we have a quantum verifier? And the difficulty is that in the quantum case, it is not in general possible, it's not generically possible to rewind a verifier. And in general, a quantum measurement destroys the internal state of the verifier in an irreversible way, and quantum information cannot be copied. And of course, rewinding is a common classical technique for proving zero knowledge. But nonetheless, we do have zero knowledge proofs for NP, which are zero knowledge against quantum verifiers. And this is from a work of Watrous. And in the non-interactive case, instead, in a recent work of Packard and Sheehan, they showed that NISICs for NP can be constructed from learning with errors in the CRS model. And one of the things we show in our work is that the NISICs from Packard and Sheehan are straightforwardly post-quantum secure. And this is because simply no rewinding of the verifier is involved there. Now, a second direction that one can explore in the quantum setting is to go beyond NP. So can we have zero knowledge proofs for QMA? And now QMA is just the quantum analog of NP or MA, where the witness is allowed to be a quantum state and the verifier can be quantum polynomial time. So the most well-studied QMA complete problem is the local Hamiltonian problem. And in this problem, the input is a classical description of a Hamiltonian, which is a Hermitian operator on, say, n qubits. It is local in the sense that it can be described as a sum of local terms, each acting on a constant number of qubits. And this is a promise problem. So you're promised that the lowest energy, the lowest eigenvalue is either less than alpha or greater than beta. There's some gap, say inverse polynomial, and you have to determine which is the case. And so intuitively, this problem is in QMA because it's easy to verify that the energy is lower than alpha if you're handed the ground state. But of course, the ground state itself may be hard to find. And so there is an interactive zero knowledge protocol for QMA. This was proposed by Broadbent and co-authors. Fang Song is one of the authors in 2016. And in particular, this is a protocol for a variant of the local Hamiltonian problem. And here I'll just give you a very high level sketch of how this protocol proceeds. So let's say that we're in the case of a yes instance. And so there is some ground state, some witness, call it W. The protocol is as follows. In step one, the prover sends to the verifier sort of an encoding under some authentication code, without being too precise, of the witness of the ground state, together with a classical commitment to the encoding key, call it K. And then in step two, the verifier sort of homomorphically measures the encoded state that she receives and gets a classical encoded outcome. And this should be an encoding of a low energy outcome if the encoded state was indeed a ground state. And this outcome is returned to the prover. And in the final step, the prover proves that the encoded outcome indeed decodes to low energy with respect to the committed key K. And P does so by engaging in a zero knowledge proof for an NP statement. Now, the question that we solve in this work is, how can you make this protocol non-interactive, or at least non-interactive with possibly an instance independent preprocessing step? And so certainly step three can be made non-interactive by adding a CRS to the setup and using a NISIC for NP. And the crux is step two, where the verifier reports the encoded outcome back to the prover. So the first thought that you might have is that the prover maybe actually can predict this outcome. So the verifier doesn't need to send it. The prover can predict it. But unfortunately, because of the requirements of the authentication code, this encoded outcome is sort of uniformly random out of exponentially many. So it cannot be predicted, and the prover can't possibly send proofs for all of these outcomes. And so I'll just tell you here what the main idea is to make this protocol non-interactive. So the main idea is to use quantum teleportation. And so as odd as it sounds, this will allow the verifier to sort of measure the encoded state before she even receives it, and report the encoded outcome in a preprocessing step, which is instance independent. So the witness will actually only be teleported by the prover in the following step. And in order for this teleportation to be possible, the verifier will have to send enough EPR pairs to the prover in the preprocessing step. And we also have to make use of homomorphic encryption, and this is why we end up getting an argument and not the proof. And one of the catches when one uses teleportation is that there are teleportation errors, for those of you who are familiar with teleportation. However, these errors are classical and they can be accounted for in the prover's NIZIC. And the last thing that I want to mention is that in this work, we also separately formalize the notion of proofs of quantum knowledge. So this is joint work with Broadbent and Grillo. It's sort of a quantum analog of proofs and arguments of quantum knowledge. Informally, what I mean is that access to a successful prover allows to recover a quantum, to extract a quantum witness. And in particular, we show that our protocol for QMA is indeed an argument of quantum knowledge. So this is all that I wanted to share. Thank you very much for listening.
Okay, thank you, Andrea.
Thank you. So do we have any questions from the audience?
So I have a question about the arguments of quantum knowledge. I mean, we know there's quantum node cloning. So is this protocol in some intuitive way ensure that when you extract a quantum witness, then something has been consumed from the prover? So like we don't run into this kind of
Yeah, absolutely. So I mean, you're assuming that the extractor has access to a prover, a successful prover. So a prover that has, in particular, I mean, it might have a witness in its own register. So if you have access to a successful prover, then you're able to extract with some probability. Basically, a state. It's not actually quite the witness, but it's kind of a little bit degraded even. So it's a state that passes the verification of your QMA circuit with high enough probability, let's say.
Okay, thanks.
Yeah.
Are there other questions?
Yeah, there is a question in the chat. So it's from Guokui. I'm not sure how to pronounce the name. So there are two questions. The first one is, do you know any applications of this NIZIC for QMA protocol?
Mm-hmm. Yeah, so yeah, actually, this is something that we've thought about, but I have not personally found like a compelling application of NIZICs for QMA yet. So this is, I think, an interesting open question. And yeah, unfortunately, also for the second question, something that it's a very good question, right? Are there any barriers to achieve NIZICs without preprocessing? It's also something that we thought about. And unfortunately, the particular sort of, you could call it trick that we use here is very dependent on having EPR pairs. So one thing that might be possible, although I don't have a concrete approach, is if you allow a setup in which maybe you not only have a CRS, but you also have shared EPR pairs. So let's say you don't have to worry about starting off with EPR pairs. Then maybe there might be a hope, but I don't have a concrete approach. This is also a very interesting question.
Okay, thank you. Any more questions? Then I give the mic back to Fan.
Okay, thanks. And thanks, Andrea, again. And I don't know, since this is our last session, are there any questions for any of the previous talks? We can spend a couple of minutes. Or, okay, well, I guess it's probably running late for people from Europe. So, okay, I'll say this will be the end of this session and also today's program. And let's give all the speakers another round of applause.
I just wanted to make a quick announcement that thanks to Giorgio Marson, we now have Crypto 2020 swag. It's something you can download and print on your own t-shirt if you wish, or on a bag or on a sticker on your laptop. I'll post the URL into the chat and also on Zulip. And if you just go to the main Crypto 2020 page, there'll be a link there for downloading the files. So go make your own t-shirts, and we'll see everybody tomorrow.
Okay, please order the t-shirts. See you tomorrow.